Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to look at the Python Numpy package and linear algebra. So in this topic, we will look at the Numpy package, including constructors for vectors and matrices, operators, including for scalar multiplication, vector and matrix addition, and matrix vector and matrix multiplication. We'll also look at various other functions, including the transpose and conjugate transpose, the inner product, the determinant, the inverse, and finding eigenvalues and eigenvectors. Now first, you have already seen the arithmetic operators for scalars or doubles and complex numbers in Python. We now require vectors and matrices. Now, Python does have 1- and 2-dimensional arrays, but these are data structures. The Numpy ND array class in Python allows for the storage of vectors, matrices, and higher order tensors. Now, unlike arrays and arrays of arrays, where each item can have different types, different lengths, etc., the ND array class ensures that all objects are of the same type and of the appropriate lengths with respect to vectors and matrices, etc. Now, the constructor for a Numpy array takes either an array or an array of arrays, each of which must have the same number of entries. So for example, here the first generates what we would consider the vector 0, 3, -1, the second 2, -4, 5, and now we have two matrices. And so the matrices are given in row order. So again, the first row of the matrix A is 1, 2, 6, then the next row is 0, 1, 4, and then 0, 0, -2. As you can see, this is an upper triangular matrix with determinant -1, 2. The last matrix is symmetric. And again, the first row, or since it's symmetric, it's actually also the first column, is 5, 1, 0, 1, 6, 2, and 0, 2, 4 being the last row of this matrix. We can also construct a complex matrix and complex vectors. So for example, here we see the complex matrix C, where the first row contains the entries 5 and 1 plus 3j, while the second contains the entries 1 minus 3j and 7. As you may observe, this matrix is conjugate symmetric. That is, the matrix is equal to its conjugate transpose. The two vectors we have are w, which is 2 plus j, but again, note that we write 2 plus 1j, just to ensure that in case the variable j is assigned, this is not interpreted as 2 plus the variable j. The second entry is 3 minus 2j. The second vector is 1 minus 2j and 2 plus 3j. You can also determine the shape of these objects once they are in existence. The shape returns the number of dimensions as a tuple. It's assigned to the attribute shape, and these tuples describe what is being stored. So for example, u and w are vectors, and therefore shape is assigned a tuple containing one entry, while A and C are matrices, and thus will have tuples with 2 entries. So the output of these 4 commands is just, again, the tuple containing 3 and the tuple containing just the entry 2 for the dimensions of u and w respectively. A and C are matrices, and so A is a 3 by 3 matrix. The first is the number of rows, the second is the number of columns, and C is a 2 by 2 matrix. You can also categorize the object based on the length of the shape as to whether or not it is a vector or a matrix. So the length of the tuple for u and w is 1, while the length of the tuple assigned to shape for the matrices A and C is 2. You can actually have higher dimensional ND arrays. These are representing tensors, which, by the way, is way beyond the scope of this course. Now, scalar multiplication and vector or matrix addition can be performed with the arithmetic operators plus, minus, times, and divide, where divide requires that the first or left-hand operand is a vector or matrix, and the second is the corresponding scalar. So suppose we wanted to calculate 2 times u plus 5 times v. That's exactly the notation we use. And so in the case of the vectors assigned previously, the result is 10, negative 14, and 23, and you can go back, review, and check that answer. I can also take a linear combination of matrices. So here we're taking negative 2 times the matrix A plus 3 times the matrix B, and there is the corresponding output, which once again you can check yourself. We can also, of course, take linear combinations of complex vectors where the coefficients themselves are complex numbers. So in this case, this linear combination of these two vectors is this vector here. Now notice we subtracted 3 plus j times the vector x. We could have just as easily added negative 3 minus j times the vector x in that last arithmetic expression. Now, matrix vector products and matrix product require the use of the at operator. And this does look a little bit odd if you haven't used Python as much. So if we want to multiply the matrix A by the vector u, again, we just perform A at u. And now the output is going to be a vector, and you can check yourself that this is indeed the product of the matrix A times the vector u. We can also square the matrix A. So you'll recall that the matrix A was upper triangular, and you will note that the square of the matrix is also upper triangular, and the entries on the diagonal are the squares of the entries that were on the diagonal of the matrix A. Of course, you can always assign the results of any of these arithmetic operations to other local variables as required. We are simply printing them so that you can observe what is actually going on. We can also, of course, multiply two separate matrices together, B times A, and that gives that matrix there. And we can either calculate first B times A and then multiply that by the vector u, which gives this result, or we could multiply the vector u by the matrix A and then multiply that resultant vector by the matrix B. And of course, these two must give the exact same answer. Now, if you're interested, you can always try and observe that B multiplied by A is not the same as A multiplied by B. In this case, it's possible because they are both operators on R3. Now, it's important to remember that the at operator is used for matrix vector and matrix multiplication. If you were to use the star operator for matrix or matrix vector multiplication, it actually performs element-wise multiplication. Thus, be very careful and be aware. So for example, if we multiply the matrix A by the vector U, we get a matrix back. In fact, what has happened is each row of A has been multiplied by the corresponding entry of the matrix of the vector U. A times A simply squares every single entry in the matrix A. B times A just multiplies the corresponding entries of both B and A together. B times A calculates the element-wise product of the matrices B and A, and then each row is multiplied element-wise by the entries of U. Humorously enough, this is equal to multiplying each of the entries of A element-wise, row by row, with the vector U, and then multiplying by the matrix B, again element-wise. However, this has nothing to do with linear algebra, but the issue is that you will, on occasion, accidentally use the star operator when you mean to use the @ operator, and things may appear as if they're working, but they're not, because the calculations are incorrect. Now, in order to find the transpose or conjugate transpose of a matrix, we use the following. For a real matrix, we can just access the capital T attribute. And in this case, that is the transpose of the matrix A. You'll recall that the matrix A was upper triangular, and thus the transpose is going to be lower triangular. Matrix B was symmetric, so there's actually no change when you calculate the transpose. And if you have a complex matrix, if you want to calculate the conjugate transpose, we first have to conjugate the matrix, and given the conjugate of each of the entries of the matrix, we then take the transpose. However, you may recall that the matrix C was already conjugate symmetric, and so in this case, the conjugate transpose of C is equal to the matrix C itself. Now, it's important to remember here, you could calculate the transpose of a complex matrix, but there's no significance to the transpose of a complex matrix. The transpose is the adjoint of that linear map. Specifically, the adjoint is that operator or map such that A times a vector U inner producted with a vector V is equal to the inner product of U and the adjoint of the linear map times the vector V. So that is the only purpose that we will use the adjoint for, and the adjoint of a complex matrix is the conjugate transpose. Now, to calculate the inner product, just simply start using the v dot function from Numpy. V dot will conjugate the first entry if it is a complex vector. So for example, we have the inner product of vectors u and v, which is the real number -17. We could, of course, also calculate A applied to u, inner producted with v, to get 14. Now, A was not symmetric, therefore it's not self-adjoint, and so if we bring A to the other side, then we get a different result when we calculate that inner product. If we want the same result, we must multiply the vector v by the transpose of A, as the transpose is the adjoint of the 3×3 matrix A. So that, again, equals 14. Now, the matrix B was symmetric, and therefore self-adjoint, so it doesn't matter whether or not I apply b to the vector u or to the vector v, the inner product is going to be the same, in this case negative 48. Now, w and x were complex vectors, and so therefore the inner product of w and x is equal to the conjugate of the inner product of x and w. And we see this right here, where the inner product is the conjugate. Finally, the matrix C was conjugate symmetric and therefore self-adjoint for complex matrices, and therefore the inner product of C applied to W and X is equal to the inner product of W inner producted with C applied to X. And again, we see that both results are identical. Now, to calculate the determinant of a matrix, we use the det function in the linalg subpackage of Numpy. So, for example, we can calculate the determinant of the matrix A. Now, you will recall that the determinant of the matrix A would be the product of the diagonal entries, as A is an upper triangular matrix. The diagonal entries were 1, 1, and -2, and thus the determinant is -2. The determinant of the matrix B would require a little bit more work to compute, but if you were to compute it exactly, it would be 96. However, because floating point numbers are being used in calculating the determinant, the answer is only ever so close to the correct answer. However, that's okay, because for all engineering applications, this approximation is more than close enough. The matrix C was self-adjoint, and you'll recall that all of the eigenvalues of a self-adjoint or conjugate symmetric matrix are real, and the determinant is the product of the eigenvalues. Consequently, the determinant of the matrix C, the product of the eigenvalues, is guaranteed also to be real. Now in this case it's 24.999 and so on, and if you were to calculate the exact determinant it would be 25. But once again, for all engineering applications, this is more than sufficiently close. To calculate the inverse of a function, we use the inverse function from the linalg subpackage of Numpy. So, for example, in calculating the inverse of the matrix A, we see that it is, again, upper triangular, as the matrix A was upper triangular. Also, you'll recall that the determinant of the matrix A was -2, and as we can see here, the determinant of the inverse is the reciprocal of -2, which is -0.5. We can also calculate the determinant, or the inverse of the matrix B, and the matrix B was symmetric, and as you can see here, the inverse is also symmetric, and the matrix C was conjugate symmetric, and the inverse itself is also conjugate symmetric. To calculate the eigenvalues and eigenvectors of a matrix, we use the eigen function in the linalg subpackage. So, if we wanted to print the eigenvalues and eigenvectors of the matrix A, you'll recall that matrix A was upper triangular, and therefore the eigenvalues are the diagonal entries, 1, 1, and -2. However, this matrix is not diagonalizable, and you'll notice that the eigenvectors corresponding to 1 are actually almost parallel to each other. There's just a little bit of numerical error here. This particular matrix is not diagonalizable. Calculating the eigenvalues and eigenvectors of the matrix B, however, give us in this case, three different eigenvalues, and you will notice that the eigenvectors corresponding to each of these eigenvalues is normalized, and if you were to calculate them, they are orthogonal to each other. For eigenvectors corresponding to different eigenvalues for a symmetric, or more generally a self-adjoint operator, are orthogonal to each other. The matrix C was conjugate symmetric, and therefore, again, we also see that the eigenvalues are real. We'll notice that there's a very small component that is complex, 3.10 times 10 to the negative 16 times j, which is essentially 0. And you will notice that the two eigenvectors are indeed orthogonal to each other, as the first entry of the entries of the first vector are 0.80669 and negative 0.18688 plus 0.56064j, whereas the second eigenvector has these entries reversed in order and the one entry negated and conjugated. Now, we can also use the output of the Eig function for diagonalization if the matrix is diagonalizable. For example, the matrix B is symmetric and therefore diagonalizable, and we can assign the result of Eig to the variable Eig_b. This is a tuple containing two entries, the first of which is a vector. What we can do now is we can call the Numpy diag function, which returns a matrix containing the entries of the argument vector as the diagonal entries of that matrix. So the first entry of the tuple returned by Eig is a vector containing the three eigenvalues. If we pass this to diag, we now get a diagonal matrix with the three eigenvalues on the diagonal. We can also assign to UB the matrix of eigenvectors. So these are normalized, and the kth column of that matrix is the eigenvector corresponding to the kth eigenvalue. Consequently, if we calculate the orthogonal matrix B times diagonal matrix times the inverse of the orthogonal matrix, which is, of course, the transpose, we get not the exact original matrix, but something very close. So as you can see, this is 5, 1 with something that's almost 0, 1, 6, 2, something that's essentially 0, 2, 4, which is, again, very close to the original matrix. You'll also remember that the matrix C was conjugate symmetric and therefore also diagonalizable. So we can extract the eigenvalues and eigenvectors, create the diagonal matrix with the corresponding eigenvalues on the diagonal entries. So here we see that particular diagonal matrix. We can then assign to UC the unitary matrix comprised of the two corresponding normalized eigenvectors. And then we can calculate UC times the diagonal matrix times the conjugate transpose, which is the inverse of that unitary matrix. And you will notice that the result is very, very close to the original matrix, which had the entries 5, 1 plus 3j, and in the second row 1 minus 3j, and 7. So following this topic, you are now aware of the constructors for matrices and vectors and the ND array class. You know that matrix and vector addition work with plus and minus, while scalar multiplication works with star and slash. You also are aware that matrix vector and matrix multiplication use the at operator. Now, you are also aware that there are numerous other functions in the package, including those for calculating the transpose and conjugate transpose of matrices, the inner product of two vectors, the determinant of a matrix, as well as the inverse of a matrix, and then routines for calculating both the eigenvalues and eigenvectors of a matrix. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!